It is always cold in my room. It will be all year. Okay, so let's talk about relationships on graphs. So I hope you see what we've done. We've talked about units and variables, independent and dependent variables, and we put that together on graphs. And then the next thing we did was we talked about how we make graphs. And then now we're ready to talk about why we make graphs. So we've learned a little bit about how, now we need to talk about why. So let's see if I can find my map. Okay. Our scatter plots show us a relationship. And the relationships are really the important part for us. In math class, you make your graph, you get the points in the right spot, you connect them with a line, a straight line, you might write an equation for it, and you're told that's all the solutions for that equation. Does that sound familiar? Okay, so you've been through that before. But when we graph in science, we're looking for a relationship. It tells us something about how the two things are related to each other. And those relationships, I know you heard Mrs. Hess say last year that it's all connected. This is the connection. The relationships are the connection. So we're looking for how those two things impact each other. So our scatter plots, they show us the relationships. And it's a lot easier to look at those scatter plots than it is to look at a table of data. Because if I gave you a table of data and said, tell me what the relationship is, would you be able to do that? Maybe if it's just a couple of points, they're in order and they're regular numbers. But what if they're decimals and you've never seen what the variables before? That makes it, and they're big numbers or they're all mixed up, that makes it very difficult for students to see the relationship. It's not like in math class where you can say, well, this one goes up by 1 and that one goes up by 2. Or this one goes up by 2 and that one doubles. Right? You've done that before in math class. That's not how it works in science. All of our data are measurements. Okay, so we look for a relationship using our scatter plot, and that relationship is our best fit line. So yesterday we talked a little bit about how we draw best fit lines. You guys had a chance to draw some best fit lines, and now we need to talk a little bit about that, all right? About what that shows us. So let's talk about correlation. Have you heard that word before? Yes. Middle school math? Yes. I want to say that that's probably the last time that you really talk about correlation. It might pop up here and there in algebra, but I really feel like algebra is more focused on how do we solve equations, how do we graph equations, how do equations work for us. We are going to talk about correlation and strength of the correlation because this is what we're going to see. You will probably never, beyond today, hear me say the word correlation. But that's what this is. That's what the discussion is. So I have a picture right here. And these are sort of the most common situations that we're going to see. Now there's one that's not on here, and I don't like that, but I'll talk about it here at the end. Okay? So we have positive correlations. Positive correlations result in lines with positive slopes. So these first two that we have here, those are positive correlations. And some of the data that you graphed yesterday, did you see any of that? Did you have lines with positive slopes? Yeah. Yes. Now, one thing I want to point out, do both of these lines look like they're going to go through 0, 0? No. I would argue neither of them will go through 0, 0. This one, it's going to go right above it, and this one's definitely not going to hit 0, 0. But as I walked around yesterday and looked at your graphs, some of you put every line through 0, 0. If it doesn't make sense, then we don't put it through 0, 0. A lot of our stuff, we have to make the decision if it should go through 0, 0 based on what we are graphing. We have to look at all of our data. All these little red dots, they look like a positive line, right? We line up our ruler or straight edge and we can draw our best fit line. Sometimes it's going to go through 0, 0, sometimes it's not. And that's okay. That tells us that either there's experimental error or the point 0, 0 is not one of our solutions. That's all it says. So do you see how these dots, they are they sort of are tight around that line. They hug that line very closely. Do you see that?
Yeah.
That's a strong correlation. We can look at just those dots without that blue line there and know that that's a straight line with a positive slope. That is a strong relationship. That's a strong positive correlation. The next one, the dots are spread farther out around that line. Do you see it? That's a weaker relationship. The more spread out they are, the weaker the relationship becomes, because I could argue that that's not the right place for that best fit line. You see this one dot way down here? Maybe the end of this line should be farther down. It's harder to put our best fit line in because the relationship is weaker. Does that make sense to you? So then we have a negative, positive correlation means that they move together. The variables move together. When one variable increases, the other one does too. So as this variable gets bigger and bigger, then the point up here, this variable has to be really big too. So let me see if I can come up with an example here really quick, just off the top of my head. Temperature and, I don't know, as temperature increases, what else increases? I put you on the spot. I put myself on the spot. Let's see. Let's do it that way. Let's use time instead. As time increases, age increases. Right? So let's say for this graph is just for me. Time started a long time ago, right? My age started shortly after it, but as time goes forward, my age goes up. Time gets bigger, my age gets bigger. Do you see the relationship? That is a positive correlation. As one variable increases, the other one does too. And we know that's true because as way out here on our time axis, I'm way up here on my age axis. That's where my point is. Do we see that? Okay. So, that's a positive correlation. For a negative correlation, they move opposite of each other, and we end up with a line of a negative slope. So we have examples here of a strong negative correlation, a weak negative correlation, and a moderate negative correlation. We talk about strong and weak. If your data looks strong, then I know you've probably made up your data. Okay, I've been doing this for a while. I know what your data should look like as we start the year and as we go through the year, and it's going to look more like this, and maybe we'll get to this. Okay, and that's okay. But when we have a strong relationship, just like we talked about with the positive one, all of the dots hug that line. As we get weaker, the dots spread out more. But there's some middle ground where the dots are kind of spread out, but they're still kind of around the line. That's the moderate relationship. We really don't talk about that very much. But can you see that these dots, they have a natural negative slope to them? So we have to make sure that we draw a line with a negative slope. We do not make it go through 0, 0 if it does not go through 0, 0. If I drew my line like this, does that make any sense at all?
No.
Not at all. There are no points that tell me that that's the way my line should be drawn. We always go with our data. Even if our data is completely wrong, we always go with our data. The data is our evidence that we use. Just like in English class, you use textual evidence. In science class, we use evidence. It's our data. Okay? When we have a negative correlation, our variables move opposite of each other. So if we look at this line up here, when my horizontal variable is really high, see how it's way out here at this point? My vertical variable is low. And that will always be the relationship for a negative correlation. One will be high while the other one is low. Or this one is low for this dot right here when the vertical variable is high. These two, they're big together or they're small together. This is one of each. One's big while the other's small. How do we feel about that? Good? Okay. So then the last one we have here, and I hate this graph. This is more of a statistics thing. That's not a science thing. No relationship. There's no correlation or zero correlation. There is not anything. What do we typically see when there's no correlation? What did I tell you the other day? It's a horizontal line. So when we have a negative correlation, it is a horizontal line. And I want you to write that down. No correlation or zero correlation. It is a horizontal line. You did. Yep.
These are the ones I don't really remember.
Okay.
So I have my names on those two pieces, the one that's seven and the one that we went up.
Okay.
They have to go out both front and back.
Okay.
I send transcripts for kids that I feel to me.
To
I
be
have
a
the transcript on file. There's only more in them.
Okay. Yeah. I'm surprised that would sign up.
GPA.
Yeah, okay. Great. Thank you. Yep. Okay, so horizontal line, no relationship. Horizontal line, no relationship. That horizontal line, so when we have a positive correlation, our points are big together or they're small together. For a negative correlation, one's big while the other one's small. For no correlation, no relationship at all, that means our independent variable, as we change it, it does not affect our horizontal variable. It does not affect our dependent variable. As we change the independent variable, our dependent variable is not affected. We get a horizontal line for no effect. Do you have any questions about that? We're all good. Okay. Let's see what's next.
I know, that's what I'm looking for.
So, you guys had an opportunity to graph. I gave you data, you made your graphs, but now we have to write a relationship statement. So, a relationship statement is a sentence that explains the relationship clearly. That's it. Scientists are not real creative sorts, right? We just call it as we see it. It is what it is. So here's the key though. It's got to be clear. And this is something we really have trouble with. So I want to make sure we really understand this as we move forward. So here I have an example of a graph. It's already graphed for you. I tried to pick one that is graphed correctly. We've got a title, we've got axis labels. The only thing that's missing is there should be a $sign in parentheses here, or the word dollar in parentheses. It starts at 0, 0. I thought this was a fairly good one to start with. Okay. Now, is this a strong, moderate, or weak relationship? It's really strong, right? The points are really, I mean, they're all touching the line. This is a strong relationship. Okay, so let's write a statement of this relationship. Can we all agree that this is a linear relationship? All right, and this is how you're going to write your relationships every single time. I think that purple marker is dead. So let me use something that's not blue. All right. You ready? As, then we're going to fill in our independent variable. What is our independent variable? Bridge length. As bridge length write while I'm writing, you can write after we're done, but I want you to pay attention, okay? So as bridge length increases, comma. Now we're gonna fill in our dependent variable. What is our dependent variable?
Painting.
Painting cost. What does it do? It increases. See how this is a positive correlation? That means that they move together. When one gets bigger, the other one also gets bigger. So as bridge length increases, painting cost increases. Period. That's it. Now, I'm going to tell you that you should go back and check it. Students sometimes completely disregard that, and it often gets them into trouble. So if we start at, let's say, 100 feet of bridge length, so here at this point, our painting cost is just under 20,000. Can we all see that? Okay, 18,000. At about 100 feet of bridge length, we have about $18,000 worth of painting cost. If we increase from that, let's be crazy and go up to 400. If we increase to 400 feet of bridge length, does our painting cost increase?
Yes.
Yeah. So quick, easy check, right? Now we're up to what? 65,000. That's probably 67,000. So this statement is true. This is the statement of relationship. How do we feel about that? Good? It is easy. But I will tell you, and I have several students in here who've been in my classes before, and I think they will agree, that it doesn't matter if it's really easy or not. You'll make it harder than it has to be just because you think it couldn't possibly be that easy in Mrs. Foley's class. Right? I mean, that's what happens. Any questions? I don't know, this might be the last one. It's always a struggle. Okay, we have another one. So I want you to take a minute, and you don't have to necessarily write the statement down, but I want you to think about what it would be, and then we'll go over it. All right, are we ready? Okay. So, we're going to start the same way we did last time. As. What's my independent variable? Hours of exercise per week. If you want to rearrange that and make it the same thing but shorter, that's fine with me. Weekly exercise hours, whatever, I don't care. So, hours of exercise, I drop words all the time, the words that aren't important, per week. So I just want to make you aware of that. I know what I said and what I wrote are different things, but it's still, I drop words that don't need to be there. So as hours of exercise per week increases, comma, what's our dependent variable? Resting heart rate. What does it do? Decreases. All right? Period. So let's check to see if that is true. We're going to pick 2 points. So I'm just going to pick randomly off of my line. I'll pick this one here and this one here. Okay? And let me circle those because you probably can't see that colored in. All right, so here we have 3 hours of exercise per week. That is about 67 beats per minute. That's our resting heart rate. Okay, 3 hours of exercise per week. It's about 67 is our resting heart rate. So if we go out here to, let's say, 7.5 hours per week, we've increased our independent variable. What happened to our dependent variable? It's lower, so it decreased? Is that what our statement says? So we're good to go. I promise you, this is what I'm looking for when I say that statement of relationship. And I promise you, a bunch of you will not give this to me. You literally fill in the blank. This is our independent variable. This is our dependent variable. That's the recipe right there. Questions? That, I believe, is the last one. Okay, I lied again. I'm gonna stop doing that. I'm working on it. One more. This is our last one. I remember this one. So this is actual physics data. This is an actual lab that I have done in the past with my physics classes. And let's write a statement for this. So on the horizontal axis, this is, I'm gonna get rid of that. That's angle in degrees. And this says period in seconds. It's not an English period. Okay, so let's write this statement for this as, what's our independent variable? Angle increases, comma. What's our dependent variable? Period. What does it do? Increases? Increases? Period.
Do you ever use words like slightly, or like, could you say, as angle increases, period slightly increases, or do you just keep like words like that out of it? Does that make sense?
It does. I'm afraid to answer that because I think it'll muddy it for everybody.
Okay.
Because then we start throwing in adverbs and adjectives that you lose sight of the relationship itself.
Gotcha.
Okay, now, with that said, as we learn more physics, your descriptions can become more descriptive. They can become more specific. But the best answer, I think, at this point is it depends.
Okay.
It depends. So, do we agree with this statement? All right, let's pick 2 points. What do you think?
It increases.
It increases towards the end of it.
It increased by 0.1.
So, now I am right up here next to it, and I know it's fuzzy because I had enlarged the picture so you could actually see the graph itself. But it's true, like if you would have the actual data for this, this blue diamond is touching that line, that blue diamond is not touching the line right beneath it. Is that enough of an increase to say that, yes, there's an increase there? No, it's not. So you remember on the last graph where I circled 2 points that were on my line? Our line is the solution, not the points. We have to look at the points on our line, not the points that we've collected. Because our line is the relationship. I picked this graph specifically for that reason, because I always have students say, yes, there is a relationship there. And I know what you did. You looked at the beginning, and you looked at the end, and you said there's an increase. There is no increase here. This best fit line would look like this. Now, that data is experimental data. And do you remember when I told you that students don't collect the best set of data? That your data it looks like a weak correlation. This is experimental data. There is some error built into it. It's just the natural way that we make measurements. We can't make exact measurements. So that's just a natural part of data collection. That line, if I had you do this lab, you'd get a line, it would have a really tiny slope. It'd be like 0.013. Is a slope of 0.13 really a measurable slope with the ability that you have to collect data, to make your measurements? No. No. I always have students every year that are out to prove me wrong, that they're gonna collect fantastic data, and Mrs. Polly doesn't know what she's talking about. Go for it. I'd love to see it. I'm not telling you that you're not good at measuring because I'm trying to be mean. I'm telling you, just based on my data, my past years, it doesn't happen. You need to practice collecting data. There is no relationship between the period and the angle here. There is none. So, the whole point of this is to write our statement. I wanted to show you an example where we had no relationship because the statement changes a little bit. Here's what we write. There is no relationship between our independent variable, angle, and our dependent variable, period. That's all we write. So, how do we feel about that? Okay. Never-ending data sets. What? Yep. This is a little different because it's for my master's. So I would never normally tell you what lesson it is, but I have to for these people. All right, so I thought we'd keep it short today. What time is this class over? 14. 1 year I'm gonna learn it. And then that's it. Then I'm done. Okay. So what I would like for you to do is graph this data, draw a best fit line, and then write a statement of relationship. Yep. Yep. Just what you did yesterday, except you're adding the statement. Yes. Okay, let me turn this off first. Okay, we're gonna hope it's off. Or not off.